In this session, I'm going to talk about performing different kinds of calculations using R. So, to start with, once we have installed R, right, we get some kind of a screen like this. Probably let me do something. Let me close R and again start the R. When I'm starting the installation, after the installation, when I'm running R, this is what I get, right? I get some kind of instructions including the version and a few other help related things, right? If you say demo, I get some demos. If I say help, I'll get some online help, a few other things. Now this is what we will get whenever we are starting R for the first time. So this is where we actually start typing our code. Now the simple thing is, this R prompt is a straightforward thing which works like a calculator. I can use different kinds of arithmetic functions. Let's say I simply say 2 plus 3, I get 5. Right? 2 multiplied by 3 gives me 6. Or probably I can use something called logarithm of 10, gives me some value. So like this, I can enter any number of regular function. So I can use the logarithm. Just like a calculator, I can do all these things at the command prompt. Each line at the most can have 8192 characters. But let's say for more clarity purpose, I want to break it into more than one line. So let's say I want to do a 2 plus 3 plus 5, and by somehow 5 I missed out. Right? I did not add 5 here. Now you see what has happened when I pressed enter, the next line did not show a command prompt. The next line did not show a R prompt here, but it has shown a plus sign, saying that your command is not yet incomplete. It is incomplete. So especially when you have a lengthy instruction and you want to break it into one or more lines, so wherever you want to break it without completing it, you just simply press enter. So the prompt will change from a greater than symbol to a plus. So you can still continue. Let's say I want to still add 5, which is now computing 2 plus 3 plus 5. But let's understand, even if you do multiplication also, 2 into 3 into, but we did not complete it, but still you will get a plus sign here. You will not get a continuation sign. So this plus does not mean arithmetic. It means that it's an incomplete expression. You have to still complete it. Even if a bracket is open but not yet closed, you will find all this kind of instruction. Now once you have entered it, it will ignore this plus sign and simply say 2 into 3 into 5, giving you a sum of 30. Now wherever, let's say you went ahead something like this and somehow you did not want the plus sign to continue. You found that this plus sign is, you just missed out, you unnecessarily have put this star. You just need 2 multiplied by 3 multiplied by 5. And I don't want to put anything here. Then it's better that you press the escape. Once you press the escape, again the command prompt comes and you can press the up arrow to typically take you to the previously given instructions. Any of the instructions, up and down arrows will take you to the previous and the later kind of instructions. You can make the modifications wherever possible and you can very well execute the instruction. So all your previous instructions can very well be retrieved by using the up arrow followed by down arrows. Up and down arrows will take you to your last executed kind of instruction. So this is how you can very well plan out your incomplete stuff, which you can take it to the next line, and the next line will start with a plus prompt, and you can complete it with for getting a different kind of an expression. Now, I can have multiple things also executed on one single line. Let's say 2 plus 3. I put a semicolon, 4 multiplied by 6. I put a semicolon, 8 divided by 2. All of them will be executed one after the other. 2 plus 3 is 5. All separated by semicolons. They can be put on one single line and the execution can happen on one single line. 4 multiplied by 6 is 24. 8 divided by 2 is 4. All the instructions can be executed one after the other, even though they are given on one single line. Then, in many cases, what we see is, in a general scientific notation, R represents, if R is representing something as 1.2 E3, it means that 1.2 into the 10 to the power of 3, so which will become 1200. Similarly, if it gets written 1.2 E minus 2, it is 1.2 into 10 to the power of minus 2, it becomes 0.012. So we have to be comfortable when R is giving us the solution in this form, right? So some of the very basic arithmetic stuff which you can work out, it works like a calculator only. Alright. Now, if we go into different kinds of calculations that can be handled in R, complex numbers can quite comfortably be handled. We know complex number consists of a real part plus an imaginary part. And for imaginary part, generally we see a letter I, right? So probably we have, let's say I'm assigning some Z. The assignment typically goes, a variable assignment goes with some character like this or some string like this with a less than and a hyphen. So I am assigning Z 3 plus 5i. So this is an imaginary number. So Z is assigned, a variable called Z is assigned a complex number called 3 plus 5i. I can perform, if you remember any calculations associated with the complex numbers, all those calculations can quite comfortably be performed in R as well. Right? Some of them. If I want to get just the real part of it, I simply say RE. RE of Z will give me only the real part, which happens to be 3. So I am getting the real part of Z. Similarly, if I want the imaginary part of Z, I just put IMZ. So 5i, it omits the I and displays the imaginary part. Then, if you remember, A plus BI is the complex number, then the modulus of that is given by square root of A squared plus B squared. Now the same thing I can use using the mod Z. I can use mod Z formula, which will give me square root of 3 squared plus 5 squared, which works out to 5.83. Similarly, the argument of Z. The argument of Z comes out as tan inverse y by x. So the same logic, right? I can give argument of Z coming out to 1.03, which is nothing but tan inverse of y is 5 and x is 3. So tan inverse of 1.66, which will work out to the same stuff, right? So that is what is being given out here. Similarly, if I can get the complex conjugate, so A plus BI, the complex conjugate is A minus BI. So that's where the imaginary part gets changed in a complex conjugate, and probably the same thing I can execute using the C caps. So for 3 plus 5i, the complex conjugate works out to 3 minus 5i. And if I really want to check what is the class of this Z, what is the type of this Z, I simply say class Class is a function which will tell me what is the type of z. Yes, it's a complex number. And probably if I can say is complex, if I want to check whether it is complex or not, I'll use is.complex, which will give me true. Right now, if I really want to change some number which is not a complex number to a complex number, then I'll use as.complex. This is what we call as coercion. We'll look at it slightly later. But whenever I want to convert from one form to other, here any form to complex if I want to convert, let's say 3 as a number, which is a real number, I want to convert it into a complex form. So it becomes 3 plus 0i. That is what will make it a complex number. So we can handle a lot of complex numbers related calculations in R quite comfortably. Right? Then, moving on. Other common functions which we can handle in R. Rounding related, there are so many functions which we can do in R. Some of them being the floor and the ceiling. Right? Floor. Okay, if I do floor of 5.7, I get 5. Which is, it is the greatest integer which is less than this number. The greatest integer less than 5.7 happens to be 5. Similarly, for the negative numbers also, if I apply the same concept, the greatest integer that is less than this number. Right? Greatest integer that is less than this number. So it has to be less than. So probably if I am doing floor of minus 5.7, we have to be clear that we will get minus 6, not minus 5. Because we are saying there's a floor is defining the greatest integer less than the number. Whereas on the other side, if I am using ceiling, it is exactly the other way. Ceiling of 5.7 gives me the 6 because it is saying the next integer, the integer that is greater than this, the immediate integer that is greater than this. The same logic goes with minus 5.7, the ceiling will give me minus 5 because it's the integer that is greater than this number. Right? Similarly, I have another kind of a function called truncate, where I can simply truncate the decimal part and I just look at the integer part only. Or I also have a function called round. Round will probably, if you look at slightly better, if I am using a number 5.72, I can round it to one digit after the decimal point. Then I will get 5.7. But if I say round 5.77 and one digit after the decimal point, it becomes 5.8. And if I say round 5.77, 0 digits after the decimal point, it becomes 6. So it gets rounded off either to up or down accordingly. So we can use the round function wherever required. And the other important function that we use quite comfortably sometimes is the significant. So which talks about if this is a big number, if I am saying I want a significant 4 significant digits, so first 4 digits are taken to be significant. After that, the whole thing is rounded off to the nearest zeros. Right? The whole thing is rounded off to the nearest zeros. Probably if I am doing this significant 1, 2, 3, 4, 5, 6, 7, 8. Let's say I want it to the 4 digits. I get it as 1, 2, 3, 5, 4 zeros. Because it's an 8-digit number, only 4 digits need to be significant. So the last 4 digits are made 0 and everything is rounded up to the previous number. Now if you say significance for the same 1, 2, 3, 4, 5, 6, 7, 8 and say 3 only to the first 3 digits. So you say 1, 2, 3 and because the fourth digit is a 4, it does not get upgraded, 3 does not get updated to 4 and all others are becoming 0. So that's the way the typical rounding related functions are working. Similarly, you can do any kind of arithmetic. We have already seen we can do addition, subtraction, multiplication, and we have to be clear that here the BODMAS rule will be applied. So the brackets will have high priority, right? Then we are having of or exponent kind of stuff, powers. Then we are talking of division, multiplication, and then addition and subtraction. So the execution will be given in this particular order. And anything to do with the power is given by this kind of a symbol. So if I am simply saying 5 power 3, I will write it with this kind of a symbol, 5 power 3, making it 125. So I can use the logarithm to get to the base e. Exp is the kind of function that I use for exponent. So I say exp of 1, it is nothing but e power 1, which is e. So 2.718 is the value. Then if I want the logarithm to any other base, I have to refine it like this. Two values I will define in the log. So log 9 comma 3 is log 9 to the base 3. And we know that log 9 to the base 3 is 2. So it is getting calculated this way. And sqrt is one more function. Factorial is one more function. Right, I can simply use factorial of 7, 5040. So the 7 factorial, 7 into 6 into 5 into 4 into 3 into 2 into 1. So a lot of arithmetic calculations can be performed outrightly in R. Similarly, I can use NCX, typically the combination stuff, right? NCX by using the choose function. So if I want phi C3, I simply say choose phi comma 3. Phi C3 is 10. So I am getting 10. So choose is a function which is giving me the value of NCX. If I want random numbers to be generated between 0 and 1, right? I want 10 random numbers to be generated between 0 and 1 following a uniform distribution. This is where I rely on a simple formula called runif. If I say runif 10 different random numbers will be generated between 0 and 1 following a uniform distribution. So these are the 10 numbers randomly generated using a uniform distribution. Now I'll talk about the random numbers slightly towards the end of this session, where if I want to repeat the same thing again and again, probably if you see here, if I'm doing again a runif 10, I get a different set of numbers. Now, what do I do if I need to maintain the consistency in the random numbers being generated? I'll slightly talk to that towards the end of this chapter. Let's complete the remaining stuff. Then, similarly, I can get the trigonometric ratios also, the cos, sine, right? If I'm saying cos pi by 2, so which is almost 0. Right, cos pi by 2, cos 90 degrees is 0. So this is showing a very small number, though it's not exactly 0. Let's try sin pi by 2. Sin pi by 2, it's 1. Tan pi by 4, 1. So pi is simply denoted by pi. Tan pi by 4 is 1. Sin pi by 3, square root of 3 by 2. So it is around 0.866. So we can get all the trigonometric ratios being provided. Absolute ABS, absolute value of minus 3.5. The negative sign will be removed, so I'll get just 3.5. Absolute is giving me only the positive sign. So all kinds of arithmetic functions can quite comfortably be executed in R. Then the other set of common functions that I come across is the usage of modulus and integer quotients, right? Probably I want 119 divided, so let's do three things. 119 divided by 13, 9.15. Let's say I want only the quotient. I'm not interested in the remainder, or I'm not interested in the decimal part. I want only the integer quotient. In that case, use this kind of a symbol, right? Percentage slash percentage. So you say 119, instead of just putting a slash, you put 119 percentage slash percentage 13. Then I'll get only 9. The decimal part will not be shown. Only the integer part will be shown for the division. Whereas if I want only the remainder, which is what we call as a modulus, then put only double percentage. 119 percentage 13 is going to give me that the remainder is 2, which means 119 is not perfectly divisible by 3. To basically check if one number is an exact multiple of some other number, I can very well use this modulo based calculation. So if I really want to test whether this is equal to 0, right, probably I am having some big number, I really want to test whether this is divisible by 23. I simply say whether the modulus of this is 0. If it is divisible by 23, I'll get it as true. Probably you can check it like 171 modulo 19 is equal to 0. So when I'm dividing 117 by 19, because it's a perfect multiple, I'll get it as true. But some other stuff where the division is not perfectly divisible, then we are getting it as false. Because we use them in a lot of rules at a later point, so we need to be comfortable with the usage of all these different kinds of functions. Then, we have already talked about it, variables. Right? Whenever I want to assign a variable, I'm just typing some name of the variable using a less than and a hyphen, and I am assigning some values to it. So that's a variable assignment, but make sure that it is case sensitive. So if you are putting a variable z versus a capital Z, these two are two different variables according to R. So we have to be careful about it. And some of the rules that you have to be comfortable, the variable names generally don't begin with numbers, but somewhere in the middle there can be numbers. Similarly, the variable name should not have blank spaces. So either you can put underscores, or in R you can even use the dot operators. Right? Probably first name. If that is the name of the variable, either you put it like first underscore name, or probably you can use a variable name called first dot name as well. All are valid, but obviously there can't be space. And try to make your variable name as short as possible so that you don't type in big words and probably at a later point end up with so many spelling mistakes while you are using those variables as a part of the calculation. Right? So when you are representing it like this, it means that x is taking a value of 5. Now, different kinds of operators, some of them which we have already talked about, the addition, subtraction, multiplication, division, integer, only the integer quotient in a division, modulus, power, all arithmetic operators, greater than or equal to, less than or equal to, not equal to, all are relational operators. Then we will talk about this logical operators in the next session, but we can talk about or and, not. This is not, and or. Now this is the one we'll use much later when we are developing our statistical models. Right? So generally when we talk about a relationship between dependent variables and independent variables, we use the relation between these two with a tilde kind of a symbol. So in models, when we are trying to build the formulas, the relationship between the left hand side and the right hand side we build using this symbol, where we talk about y is a function of x1, x2, x3 and so on. So right now I will not be using it. Similarly, the dollar. When we create a list, at a later point I will be talking about the list and data frames, some of the complex data structures that are available in R. When we have to access some of the elements of the specific list or a specific data frame, we can refer to the dollar as an operator there. So in the regular scenarios, we will not be using the dollar operator. So let's hold on to this at a later point. Then if I want to create a sequence, probably if I want to get numbers 1 to 10, I can simply say 1:10. So sequence can very well be initiated through a colon and a few other operators which we would be using slightly at a later point, where I am using double ampersand. So it is like and with an if and only if. So this is or with an if, and we have exclusive or, either x or y but not both. That is what we are calling as XOR. So all these kinds of operators we will be using at some point or the other. We just need to know what are the different kinds of operators that are available in R. Then if I look at a few other important types, then we have integers as another important type. So let's look at this. Let me assign x some set of values. Probably now that I have talked about the sequence, or if I am giving some set of values. So if I am giving a list of values, it's better that I enclose them with a C function. C function is nothing but, or right now let me not bring in the C function. When I talk about the concatenate later, I'll bring it in. So I am giving x is 123, some number. I want to check whether x is an integer. So I'll say is integer x. But it is saying false. It's saying 123 is not an integer. Just check what is the class of x. What is the class x is belonging to? It's a class called numeric. It's not integer. By default, any number that is assigned will be given a class called numeric, not integer. So just check is.numeric of x. So it says yes, it is true. But let's say I want to convert x not into numeric, but I want to convert it into integer. So what do I do? X, I'll take as dot integer, I'll convert. So as dot is a kind of a coercion, a kind of conversion from the existing form to your required form. So when I say as dot integer, anything that is in its original form gets converted into integer, and that is getting reassigned to x. So now if I look at class of x, this time it shows it's an integer. So if I have to convert a non-integer to an integer, I can even do that kind of a process. So probably if you look at few more, I say as dot integer minus 5.7. It's saying minus 5. It's omitting the decimal part. Similarly, if I give for imaginary as dot integer 5 plus 5i, it gives only 5, but at the same time it's giving me a warning message that the imaginary parts are discarded in the coercion. So all these kind of things we need to keep in mind. Now, one of the most important data types in R, which we might not have encountered in many places. So it's better to give some kind of focus to this new data type called factors. Right? Let's create something. Let's create, first let's create something called gender. Let's understand that. So I'm creating a variable called gender, where I'm capturing the variables, where I'm capturing the values of different people. Okay, the first one is a male, then the second one is a female, the third one is again a female, the fourth one, let's say, is a male, and the fifth one, let's say, is again a male. So let's say we have captured a gender, and for that variable gender, we are giving 5 different people's gender. So there is a variable called gender which is capturing all these 5. This is what we actually call as a vector. One single name holds a series of values. So it holds the genders of 5 people, right? So when we type in gender to display what this variable holds, I get male, female, female, male, male. Let's type the class of this gender. What is the class? It says it's a character because it's a string. So in R we don't have something called string. Everything is a character. Anything that represents a string will be displayed like a character. Now, the part is I can convert this kind of representation where the values are repeating more. I can convert them into a data type called factors, right? So especially we will do it for this purpose. If there are any categorical variables in my data, let's say one column of data is just for gender, which contains only male and female. Now we have categorical variables which have very few fixed number of levels. In that case, rather than keeping them like a character like this, it's better that I convert them into a factor. What do I do for that? I'll again reassign this gender, right? Again I create a gender by saying as dot factor gender. So first I convert this kind of character variable into a factor variable and again reassign it to the variable called gender. Now let's see what is happening to this gender. It is no more a character. Now this became factor. Right? This gender has actually became factor. Now let's type what is the content of gender. Now it still says male, female, female, male, male, but it has added the levels. Only 2 groups, female and male. Right? So that is what it has typically done. That is what it has typically done when I am converting something into a factor. Right? But let's understand, whenever I am reading the data from a table, here I have entered the values manually at the R prompt. But when I am reading some data from a table through something called read.table kind of a function, which I'll talk about slightly at a later point. Whenever we are reading the values from the table, reading a data from a table, any column or a variable that contains 1 or more characters. So if any column called gender contains 1 or more characters, automatically will be converted into factors. So if I don't want to convert it, I have to have some kind of a mechanism. I'll come back to it. But by default, if at all I am capturing the data from a table, I would see that all the character variables are automatically converted into factors. And this is a very important aspect, especially when we are doing analysis of variance ANOVA or analysis of covariance ANCOVA. When we are doing them, we can really see the importance of all these different aspects. So we can, when something is a factor, we can very well use some of these functions. First thing, I can check whether something is a factor. Yes, it is a factor. True. Now when something is a factor, I can get the levels of what are the levels. So levels of this gender. So there are 2 levels. There are 2 different unique values associated with this factor, which are female and male, which I can get through the levels. And if I want to know how many levels are there, I can give n levels. N levels of gender tell me how many levels are there in gender. there are only two levels, female and male. So these are the different things that we can very well get with respect to the factors. Now if you look at the gender, right, by default it is showing female levels as female and male. But let's say I want it to show in the order which I want. By default it will show in the ascending order. Right? Though male has come first in the data, it will show female first and then the male next. But if I really want to be shown in the order which I want, then what do I do? First, let me assign the word gender. Right? Let me assign to the word gender whatever the factor. So I will create the factor. I will create a factor containing the gender, but at the same time I'll give the levels in my own ordering. So I'll say it should be equal to the same factor, but the levels here should be a combination of, first it should be male and then it should be female. Right, I am giving the word gender, the factors. So I am making this as a factor. The entire content called gender, I am making it as a factor. But I am defining the levels in my own order. Now if I type in the gender to look at the variables, you see that the levels will come in the order of what we define. Sometimes when we are doing some kind of computations, we want the order to be the order which we want rather than the default order which the system specifies. So this is what it is. By default, the factor levels are treated in the alphabetical order. And now I have shown you the example. If I really want to change it to order of my choice, what should I do? Here is some other example, but I have taken it with the same data itself. Now, when we are comparing the factors, I can use only the equal to or not equal to kind of stuff. I can't use greater than or equal to kind of things for comparing the factors. Though the factors are numbers, where internally they are converted into ones and twos, but I can't use those factors for the greater than or less than kind of comparison. So the factors can only compare to another factor with the identical set of levels or to any other character vector. Now if I really want to convert this from factors back to original, right, this is where I use the unclass function. So if I say I convert this factor into vector and I do an unclass of gender. So what happens when I am unclassing the gender? So initially whatever are the ones and twos that are assigned to male and female, now 1 is shown, 2 is shown. So unclass. So it's no more the class. So whatever the 1 and 2 assigned, 1 is assigned to male and 2 is assigned to female. So now when I do unclass, so there is no association of male equal to 1 and female equal to 2. So just 1, 2, 2, 1, 1. 1, 2, 2, 1, 1 is prepared and it is just shown as one single vector rather than any kind of a factor here. Right? So when we really want to get the numbers that are assigned to it, we need to first unclass that factor. Whatever is the factor variable, you first unclass it, because when you look at the class of gender, it is factor. So if it is factor, first make it unclass. So unclass is removing the association of the factor and then convert it into anything else of your choice. And one more important aspect in this session that I want to deal with is generating of the random numbers. we have initially discussed, if I have to design three random numbers between 0 to 1, I'll simply use run if 3. But if I do the same thing again, I'll get some other numbers. If I do it again, I'll get some other numbers. But if I want the same set to be repeated again, this is where we take the help of the function called set.seed. So I say set.seed, I'll set some initial value, let's say 100. That's the seed I'm setting, right? And now if I put run if 3, I'm getting this number 0.307, 0.257, 0.552. Now again you go to run if something else, I'll get some other set of values. But again set the seed, set seed 100, the same 100. Now again do the run if 3. You get the same set of values that you have got here. This is where you can maintain consistency. So if you are using the same seed value, right, if you are not using the seed, you will get some other set of values, right? You are not getting any matches anywhere. But again you say set.seed 100, and after that you do the run if, you get the same set of values. This is very important when we are comparing our models. So you see, whenever you have set the seed to be equal to 100 and running the run if, we are getting the same set of values every time. Then another thing is, if I want to recreate the same set of values again and again, this is where I can use .random.seed. Right, when I am assigning a particular value, so let's say I assign something to current .random.seed. Okay. Okay, I did current.random.seed. Now when I do the run if, I get the latest ones, what I got earlier. The 0.05, 0.46, 0.48. This is the same thing that got repeated again. Now again I do a run if 3. I'm getting 0.812, 0.370, 0.54. Which means the recent ones that we have recreated, all of them are getting repeated when we are using this .random.seed kind of a function. So some of the things, especially if I have to create the random numbers, because we will be using the random numbers very heavily in many scientific and statistical procedures. Even as a part of the sampling, we would be using this random numbers quite heavily. So if I am looking at the sampling process, we have two different samplings, though we will deal with them in more depth slightly at a later point. But right now, if I want to do a sampling without replacement versus with replacement, if I want to do sampling without replacement, then it means that all of the values which are there in my vector, they are going to appear in the output, but in a random fashion. Let's see, I'll assign a variable y, wherein I am defining 1, 2, 3, 4, 5, 6, 4, 8, 3, 2, 1. Let's say this is a kind of a vector. This is a set of values I have created and assigned to y. Now, if I simply say sample y, so the same set of values will be shown, but in a different order. Now you could see 3, 4, there are obviously 2 5s. Even I am seeing 2 5s here. All the numbers are shown, but their order is changed. So this is what we call as order without replacement. So all the values are being picked, but obviously no value is omitted and no value is repeated. If the value is already repeated in the original data, probably it will occur those many times, but it does not occur more than that. Now within this, if I really want just 5 values out of this sample, I say sample y comma 5. Only 5 will be pulled out from this subset. So this is a subset. So in this kind of a sampling, I'll use a simple sample kind of a function, right? It is shuffling the content of the vector into a random sequence, but all the values will be coming. There is no question of omission. Especially when I am doing the randomization in experimental design, we'll be using this concept heavily in simulation. Very computationally intensive hypothesis testings if I have to do as a part of the statistical procedures, I'll be using this kind of a sampling mechanism, right? So if I want only a small subset, I just need to mention how many I want here. Similarly, if I want to go with sampling with replacement, all I have to add as a value is y sample replace equal to true. So if I say sample y comma replace equal to true, then it means that it can pull some of them can be omitted. Now if you see in this list, 8 is not there at all. So 8 is omitted from this list, whereas let's say number 3 is repeated 4 times, whereas in my data actually 3 is present only twice. So there is a possibility some values are omitted, some values appear more than once. So in some other experiments we would be using this sampling with replacement. So we have to be very clear in what context we have to use what, but at the same time that we will be discussing at a slightly later point. But simple thing is we are looking at replacing the values. We are taking a sample of values with the replacement. So some of the values are getting omitted. If I am doing a sampling of values without replacement, none of the values are omitted. So these are the different computational related stuff that you can perform in R. Probably use it as a much efficient calculator. And when we go more and more deeper into the statistical aspects and the various data related aspects, that's where we could be using all these things at different points in different manners on that same data sets. Alright. So if you have any further queries on this, you can get back to me by giving me a call on the number that I have provided below, or you can send in an email at vamsidhar@pacegurus.com. Thanks a lot for listening to this session. Thank you very much.